In this video we will review three standard numeric systems used in computer science. These three systems are binary, octal, and hexadecimal. So starting off, we'll start with the oldest numeric system into the newest numeric system. So beginning with binary. If we look at a binary number, you can tell that a binary number is a long string of both ones and zeros. So binary numbers are also called base 2 numbers. So when we look at the three different numeric systems, we have binary as a base 2 number, hexadecimal as a base 16 number, our own system is decimal, or base 10, and octal is a base 8 system. So starting off with binary, for our simple binary numeric system, we have this right here, the founding part of binary, 1 digit. 1 digit is called a bit, which is short for binary digit. So each of these is 1 bit. Now, you can have a binary number of any length, any size, but for standards in computer science, we like to group them by 8. So when they're grouped by 8, we have what's called 1 byte. 1 byte is made up of 8 binary digits, or 8 bits. So now each of these bits can either be 0 or 1, so starting at the lowest possible value, 8 zeros, it equals 0 as a decimal number. Or 8 ones, which equals 255 as a decimal number. So there's 256 possible values for binary, 0 to 255. Now, that's binary, our base 2 system. So for a quick conversion, right here, if I gave you the number 1011, a base 2 number, this 2 right here indicates that it is a base 2 number. That way we make sure we don't read it as 1011, but as 1011. So beginning with the conversion, we have the base of the numeric system to the power of the position. So starting at position 0, we have 2 to the 0 times 1, plus 2 to the 1 times 1, plus 2 to the 2 times 0, plus 2 to the 3 times 1. So that's 1 times 1 plus 2 times 1, 4 times 0 plus 8 times 1. So 1 plus 2 plus 8 equals 11. And right here, I wrote a 10 in subscript so that we know that this 11 is not binary number 3, but base 10 number. So for right here, there's a much faster way to convert, now that we know the process to convert by hand using math. If we know that our binary number is grouped within a series of 8 bits, we can draw a conversion table similar to this, starting from 2 to the power 0 to 2 to the power 7, from right to left, and then we write the binary number into the blanks. So for this one, I provided 100111101. So when we convert it, we add the sum of each blank. So right here in the 2 to the 7th position, we have a 1. So this is 127. We have a 0, so 0, 0, 2 to the 4 is 16. So next up, we have the octal numeric system. So right here, an octal number, you can tell from our chart over here, binary is a base 2, so it only has 2 possible values, 0 and 1. Our system, decimal, base 10, is 0 through 9. Right here, octal is base 8, so we have 0 through 7, 8 possible values. So you'll see in the sample octal number I wrote here, the highest numbers are the 3 sevens, because 8 cannot be used as a value, the octal system. So for octal, a simple octal conversion would be right here. So originally it was found inefficient because binary numbers used to be the only way to program a computer, so they would put in each individual number as in 1 bit. They would flick a switch to turn current on or off. But in order to read these numbers, you would have to have increasingly large amounts of switches, and it would take much longer to convert. That's why they originally grouped them into bytes, but finding a faster conversion method, they reverted to octal in many applications. So octal, right here, if I provide the number 572 in base 8, the same method as above, the power of the base to the power of the position. So base 8 to the power 0, 1, and 2 times the numbers respectively 2, 7, and 5. And then added together, 2 plus 56 plus 320, giving us 378 as a base 10 number. So 572 in base 8 is 378 in base 10. Now, for the groupings of octal numbers, why these came into play? If you notice right here that 3 ones in a binary base 2 number, 111, is equal to 7 as a base 10 number. 7 as a base 10 number is the same as 7 as a base 8 number. So we've determined that 3 ones is equal to the max value of a base 8 number. Therefore, a 3-bit grouping of 000 to 111 is the same as 0 to 7 in base 8. So octal is no longer used in almost any application other than a few where they are used for display-based applications, drawing the graphics to your screen, but nothing that would be handled by anything other than extremely low-level text anymore. They're only used in graphical calculation. So now, the system that replaced octal is hexadecimal. So hexadecimal, our base 16 system, is from 0 to 9. And then to get the other 6 values that would be necessary, we have A, B, C, D, E, and F, giving us 0 through F, where A is 10, B is 11, 12, 13, 14, and 15 for F finally. Now, right here, we have our hexadecimal number, A4FB, as base 16, indicates base 16 because it is hexadecimal. So here I convert 16 to the power of 0, 1, 2, 3, just like the others, based on their position in the base of the numerical system, times B, E, 4, and A. Now you can't multiply by B because we do not recognize B as a number, therefore we translate B into 11, F to 15, and A into 10. Now in converting this leaves us 11 plus 240 plus 1024 plus 4960, resulting in 42,235 as a base 10 number, represented as only 4 digits in base 16, A4FB. So where base 16 comes into play is when we have a group of 4 binary digits, 1111, it represents 15 in base 10, which is the maximum of the hexadecimal system, and F. So if we have a group of 4 bits, from 0 to all 1, it's the same as 0 to F in hexadecimal. This is used mainly in a lot of graphics applications, because in art we do RGB color tables. Sometimes there's others, HSL for hue, saturation, luminosity, CMYK for cyan, magenta, yellow, and black for printing standards. But in most digital art formats, we use RGB as the default table. Now, RGB, the original graphical table, each value, R, G, and B, is a number from 0 to 255. You'll notice I've also written alpha. Usually alpha is just an opacity value, so we don't work with it too much, but occasionally some images will have alpha values for them, such as PNG images. So, each value being from 0 to 255 happens to be the maximum 1 byte. So the maximum of 1 byte, 11111111, is 0 to 255, giving us broken down as 2 4-bit numbers. Each 4-bit maximum is F. So if we have 2 Fs next to each other, a series of 8 ones in binary is the same as 2 Fs in hexadecimal. This becomes used mainly in web design where they use hexadecimal color codes. So right here we have our first hexadecimal color code, indicated by the hash mark, FFFFFF. They consist of 3 hexadecimal numbers. Each grouping of 2 can represent a maximum of 255, which fits in perfectly for R, G, and B. So a series of 6 Fs in a hexadecimal color code is represented by either black or white, depending on the color system you're using. So hexadecimal, being the main standard of today, is used mostly in graphic applications. So here's an application, for example, paint.net, a freeware that can be used. Let me full screen this. So paint.net, if I bring up a color table, when I look at the base RGB values for red, green, and blue, if I drag the slider all the way to the maximum, they're represented by 255, its brightest, 255, its brightest, and 255, its brightest, which as a hexadecimal number gives us FFFFFF, 6 Fs, writing in white. So this should allow you to easily convert between RGB values to hexadecimal color codes for when you use web design where they're mainly used. Now that is it for numerical systems.